Stan Gibilisco here, proprietor and operator of amateur radio station W1GV Whiskey 1 Golf Victor, located in the Black Hills of South Dakota. And I have another little Murphy's Nemesis tale for you. This doesn't directly relate to amateur radio because it involves the frequencies below 9 kilohertz, which to the best of my knowledge are not allocated to anyone by the Federal Communications Commission. At least they weren't back in the 1970s when I did this experiment. Now, if you want to watch one of the other Murphy's Nemesis videos that I've made recently, you'll find a VLF converter that I devised with my Drake T4X and R4A radios, using them to make a VLF converter. And I was able to listen all the way down to DC using that thing. Well, actually within about 2 or 3 kilohertz of DC, that is to say frequencies 2 or 3 kilohertz, the carrier from the transmitter kind of desensed the receiver and I couldn't really hear anything much, although I could just listen to the sound directly in AM on the receiver and hear audio below 2 or 3 kilohertz if I so desired. But all I really heard down there below about 9 kilohertz was a great deal of dirty electricity artifacts. I've also made some videos about that phenomenon. The power lines don't just emit a single 60 hertz signal, as it were. They emit a lot of garbage, all the way up sometimes into the high frequency range of the electromagnetic spectrum, the ham radio bands, sometimes even up on 10 meters you can hear that stuff, but it's really bad. Down below 9 kilohertz, just overwhelming. Murphy really got that part of the spectrum for a variety of reasons, and one of them is that dirty electricity. Well, I didn't have the means to go out far, far, far away from civilization, where you wouldn't get any of that, although maybe I will someday now. I've been contemplating it. But I developed a way to cancel a lot of that stuff out. And I even built a little transmitter with a vacuum tube that transmitted from 2 kilohertz up to 9 kilohertz. I could adjust that thing with a little VFO in there, put it in a beautiful little wooden box with an aluminum panel on the front. Oh, I was in business. And this thing used a 6C4 or some weird old antiquated vacuum tube and a power supply and the whole deal. About a watt, I guess it would put out. And I tried to transmit with that thing from a few blocks away and pick that signal up on, say, 7 kilohertz. And I did it. But I got a lot better signal-to-noise ratio and defeated Murphy again to a certain point with the circuit that I'm going to show you now, a noise-canceling antenna. Murphy, take that. Okay, so here's how this thing worked. Noise-canceling antenna. Specifically designed for very low frequencies, or VLF, or very long wavelengths, VLW, and that's the key to the operation of this thing. Now here's what I basically did to start with. I had my antenna, which, as I have told you, was a 20-meter ground plane antenna fed with coaxial cable, and I left the shield of that coaxial cable intact for this application. This antenna then went to a transformer, basically an audio transformer like this, and thence to the chassis ground at the radio station. This audio transformer I don't recall whether it was step up or step down. I really don't recall. I suppose it was probably a step up transformer because the microphone input of the radio to the mic input of the T4X transmitter in AM mode. So that's how it worked. This, of course, also going to ground. Well, or at least that's the way that it went at first. But here is the key to making this thing work. This transformer had a center tap. So what I did was I connected that ground to the center tap of this transformer instead of the other end, like that, leaving the other end free. Now that gave me 2 points, one right here and one right there, that would be in opposite phase with respect to each other. Phase opposition. Now, maybe I've made a video that expounds on the difference between phase opposition and a 180-degree shift in phase. But phase opposition just basically means upside down, so that this input would be upside down with respect to the one on top. Let's make that one green. Okay? So now we have these 2 points in phase opposition. Now this antenna was receiving, besides signals, a lot of garbage at low frequencies, and particularly below 9 kilohertz where I wanted to listen. But even all the way down into the VLF band, 10 to 30 kilohertz, there was a lot of this electrical, dirty electricity garbage being picked up, and it just was awful. There was no way I was going to hear anything down on those frequencies below 9 kilohertz if it was weak. No way. So what I decided to do was to create a little trick inside the house, right up near all that offending electrical wiring. I installed a wire just running around the house, and this was my noise antenna. That was designed to pick up noise, but not much signals, because it wasn't outside, it wasn't up in the air, it was inside the house in the basement, where a whole lot of noise would be, but not much signal. So I said, okay, suppose that I install a potentiometer in series with this antenna like this. Potentiometer like that. Now that potentiometer would vary the amount of noise that I could insert into either one of these 2 points. Just for extra isolation, I put a capacitor here. It was probably about 0.1 microfarads. It was a pretty good sized capacitor because of the low frequencies. And then I put a switch in that circuit, and that switch would let me install noise in one or the other of these 2 points. So I could take my pick between these 2 points and put that noise in either the bottom or the top of that transformer like that. The idea here was that I wanted to try and get phase cancellation of the noise from this antenna with the noise from that one by adjusting first the phase and then the amplitude by means of this little switch here. So I played around with that notion, and I actually got the doggone thing to work, and it probably reduced the noise by something on the order of 20 dB, maybe even 30 dB, as shown on my S meter in my Drake R4A, something like 20 to 30 decibels. That would be on the order of 4 to 6 S units down. So say, for example, from 10 dB over S9, it would go down to S7 or S6. From S9, it would go down to S3 or S4, something like that, way down. So I was actually able, and then when I tested with my little transmitter that I described, that little tube box thing, it did not attenuate the signals any, but it did attenuate the noise. The trick is you have to pick the right phase. Now there's another trick to this that I should mention. This will work at VLF because the wavelength is so long that you can be pretty sure that the noise or whatever signals or whatever energy this antenna picks up at that wavelength will be either in or out of phase with what comes in the antenna. At a higher frequency, say 40 meters or 80 meters in the amateur radio bands, the wavelength is a lot shorter, and you can't be sure that these are going to be anywhere near out of phase or in phase with each other because of this physical separation. The only way you could be sure of that would be to put them right up next to each other, and then it wouldn't work because you'd be canceling the signals right along with the noise. So the lower the frequency, the better this scheme is going to work. And it sure worked at VLF. So Murphy got into this system, and to the tune of 20 or 30 decibels, I got her out. Take that. Until next time, 73, and so long.